This is Daniel Cusberry, and in this lecture, we're going to start looking at how we're going to graph linear functions. So the first thing we're going to do is look at the xy coordinate plane itself and just some different pieces of it. So this is what we're looking at here. The coordinate system, we'll call it the rectangular coordinate system or the xy plane or things like that. Simply two number lines that are stuck on top of each other, and they make a right angle right here. So here's a number line going from negative whatever to positive whatever. Here's another line going from negative. And so with those two number lines, you're able to plot things using two numbers instead of one. So we're going to use ordered pairs to plot things, which means we're going to have, in order to put a point on this plane, we're going to need to have an x coordinate and a y coordinate, hence the pair. We have two things. We have where it is on this horizontal number line and where it is on this vertical one. So we're going to call the horizontal number line the x-axis and the vertical number line the y-axis. Those are just conventions. Those are just universally understood. We'll call this the x and that the y. We also notice that when you have an x and a y-axis, it divides this whole plane into four quadrants. There's here, 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 and here, and those quadrants have names. This is quadrant 1, quadrant 2, quadrant 3, and quadrant 4. And so we can talk about properties of them, but just so you've kind of seen that before. And then the only other term worth mentioning right now is there's one special place where the two axes intersect, and that's the origin right here. Right here. So when I talk about the origin, we're talking about this point right here where it's, we'll call that 0, 0, and we'll kind of look at that in a sec. So let's just kind of remind ourselves how we're going to plot things on the rectangular coordinate system. So we have this first one. There's our first ordered pair. Remember that the ordered pair, the order matters. So the first number is what we call the x-coordinate. So that's where it's going to go along the x-axis. So this first number is 4. So we're going to go out to 4 on the x-axis. And then the second number is the y-coordinate, and that tells us where we're going to go on the y-coordinate. So that tells us we're going to go 2. So this means we're going to go to 4 on the x-axis, 2 on the y-axis, or we're going to go to the right 2, well, I'm sorry, to the right 4 and up 2. And so that's going to be that point right there. And maybe we can call that A. And then we can do the rest of these in a similar way. So this first number in B is negative 3. So we're going to go left 3, go to negative 3 on the x-axis, and then down 1. This is negative 1 on the y-axis. So this is where B is. So graphing is not a terribly challenging thing. I'll tell you the most challenging thing is actually getting these numbers switched or forgetting which one means left and right and which ones means up and down. That's why I kind of wrote this here, and if it helps, you can put X and Y here, and maybe that'll help you kind of keep straight which number means which. So with C, this means we're going to go forward 5, and then the 0 here means we're going to not go up or down. We're just going to stay at the 0 on the y-axis. So it's actually right here, sitting right here on the line. 5, 0, you go to the right 5, and then up 0, or just stay right where you are. And then D, the first number is 0, so we don't go left or right. We just stay right here where this vertical line is. We don't go left or right. The second number is negative 1, so we're going to go down 1. We're going to go to negative 1 on the y-axis. So this is where D is. And then E, we have 4 and negative 2, so that's over here. So we're kind of trying to get a few in different quadrants. And then F is 0, 0, so we don't go left or right, and we also don't go up or down. So F is the origin, and that's always going to be 0, 0. So that's kind of how you go through plotting some points on the rectangular coordinate system. The reason we're doing this is so that we can eventually plot linear equations and other kinds of equations. And so here I have an example of, this is not a linear equation, it's just an equation with an x and a y. And I'm going to show you how to plot this using the point plotting method. So if you're asked to just graph this equation, regardless of what the equation is, if we have an x and a y, we can use this method. And so typically how we would start, and I did a lot of this work beforehand, and so I'm just going to kind of talk about it and maybe circle some things. But how we would start is by picking out some x coordinates that are going to be easy to do math with, so some small numbers that aren't like fractions or anything. So here I went ahead and picked out negative 3, negative 2, negative 1, 0, 1, 2, and 3, some kind of small numbers that are all right next to each other, and I put them in order, which is going to be helpful when we graph. So, but I picked these out. Like these, I could have picked out any numbers, and I picked out some kind of reasonably small, easy to do math with numbers, and I stuck them in order. And then to get the y, so these are my x coordinates. So when I look at my ordered pair x, y, these are my x coordinates. I just made them up. I picked them. Now, I don't get to pick the y coordinates. I get to use this equation to find out what the y coordinates is. So for each one of these x values, I'm going to plug in x for x. So here I'll plug in -3 for x. So that's what I did right here. So this says I take 4 and subtract x squared. Here I'm taking 4 and subtracting -3 squared, and that gives me -5. And I'm going to do this for each one of my x's. So again, what I'm doing is I'm picking out the x values, in this case -3. I'm plugging it in for x, and then I'm seeing what y is equal to. So y is equal to 4 minus x squared. In this case, it's -5. So that gives me an ordered pair -3, -5. So I stuck -3 in, and -5 came out. That's kind of how that works. Okay, same here. I stuck -2 in. 4 minus -2 squared is equal to 0. So that 0 is what it's equal to. So I get -2, 0. So -2, 0. And then you can look at the rest of these if you want. I'm going to go ahead and kind of work on plotting this, but this -1, 3, so on. We get these numbers in the same way. So once we get as many ordered pairs as we want, we can graph this function. So I'm going to go ahead and just put these on a graph. I'm going to put -3, -5. That's somewhere down here. -2, 0 is right here. -1, 3 is up here. Nope, that's not 3. It's right here. 0, 4 is right here. 1, 3 is right here. 2, 0 is right here. And 3, -5 is down here. So what I've done is I went ahead and graphed 7 points. And now you can kind of see the shape of this graph. It's a upside down parabola, so I can connect these dots kind of based on what I see. I missed this point right here. That looks like that. And like that. Sorry, bad drawing on my tablet. But anyway, that's what we call the point plotting method. So again, the way we did it was we picked out some points, and usually 0 is a good one. Usually, this is probably just a good set of points to use, but you could pick out any x's. You plug each x into the equation and see what y is equal to. And that gives you your x, y, x, y. So you notice how my x's are -3, -2, -1 in order. And my y's are whatever came out. So that's how you would graph using this particular method. Okay, we're going to look at some function notation, which is going to help us graph too. And I'm going to show you kind of a visual that is often used before, but we're going to call functions by certain letter names. And so you might see like f of x or something like that. And functions can often be thought about as these machines in which you throw stuff into this machine and it comes out and it's been changed. And so we might have a function and we call it f, and we throw like the number 6 in there, and it goes into the machine, and it comes out looking different, and we'll call it like f of 6. So whatever you put into this function, we'll call it like the input or just some number, and then what comes out of it is f of that number. So we'll read it not f times 6, but f of 6. So in this case, this might be better understood with like some actual function. So here's a function, g of x equals x squared plus 1. So what this means is whatever x is equal to, so g of whatever that x is, I'm going to square it, and then I'm going to add 1. So in this example, it says find g of -3, which means I'm going to let my x equal -3. I'm plugging in -3 to that function, which means I'm going to square it, and then I'm going to add 1. So if I do that order of operations, I square it first, I get a 9, then I add 1, and I get 10. So g of -3 is equal to 10. And I could have picked any sort of input, but this said -3. So if I asked for g of -2, you do the exact same thing. You plug in -2 for x and spit it out. So here's a different function. This one looks very different. F of x is equal to 2x divided by the absolute value of x. It's still a function. You plug in some value x, and then you just kind of see what comes out. So this asks for f of -6. So what I'm going to do is I'm going to do f of -6, and wherever I see an x in this function, I'm going to write -6. So 2 times x, or -6, divided by the absolute value of x, or -6. Okay, so my numerator becomes -12. The denominator is the absolute value of -6, which is 6. And this simplifies to the number -2. So f of -6 is -2. So again, all I did was I plugged in -6 everywhere I saw an x. So I put it there, and I put it there, and I just figured out the number. So f of -6 is equal to -2. This is not that different than what we just did where we stuck in an x and we found out what the y was. But now we're calling the y f of x or g of x or something like that. So oftentimes you'll see these things substituted. So y is the same thing as f of x in a lot of cases when you're graphing things. So let's look at an application problem. So here we have a function, and it's a pretty kind of specific one. This function models the number of accidents, f of x. So this tells us that whatever number f of x is at any given moment, it's the number of accidents per 50 million miles, so that might be important to you, driven as a function of the driver's age x. So we're calling the driver's age x. So whatever x is in a given moment, that's talking about the driver's age. If x is 35, that means 35-year-old drivers. So let me start back again, read the beginning. This function models the number of accidents, using f of x, per 50 million miles driven as a function of the driver's age x in years, where x includes drivers from ages 16 through 74 inclusive, meaning they can be 16 and 74 at any number in between. And then here's the graph shown. So this is the function that's used to kind of model the number of accidents per 50 million miles that involve these certain aged drivers. So anyway, we're just going to answer this one question down here, and I've kind of already written out the answer just to save some time, but this is find and interpret f of 20. And then it says identify it on a graph. So we can find f of 20. It's not going to be that hard because we did something like this on the last example. F of 20, I already did it right here. F of 20 means you're just going to take this function, or this function here, anywhere you see x, you're going to plug in 20. So that's what I did. I did 0.4 times x, there's the 20, squared, minus 36 times x, there's another 20, plus 100. And I just did that in my calculator. I typed it just like that, and it spat out 440. So f of 20 is equal to 440. Now let's go back, because we're going to have to interpret this. Let's go back and see, what was f of x equal to again? Oh, that's the number of accidents. So f of 20 is the number of accidents. There's 440 accidents. And then we got to interpret the x too. So x is the driver's age. So when x is 20, that means we're talking about 20-year-old drivers. So with 20-year-old drivers, we have 444 accidents per 50 million miles. So this is how we are interpreting this. X means one thing, f of x means another thing. So when there's 20 drivers, you have 440 accidents per 50 million miles. So I went ahead and kind of wrote it down here. I wrote pretty much that. And this is kind of a weird sentence. For drivers who are 20 years old, there are 440 accidents per 50 million miles, which is true. It's a fine interpretation, except we don't really talk like that. So it's just a little weird. So after I wrote it down, I thought, let me say this in a more natural way. 444 accidents per 50 million miles are caused by 20-year-old drivers. So I just kind of took this same thing and made it look a little more reasonable. But this is how we would interpret this. And I got this interpretation from how it explained this function to be. So it told me what f of x was, it told me what x was, and with those two things, I was able to interpret these two numbers, the 20 and the 440. All right, there's a few other things I want to show you. This example asks us to graph two functions on the same rectangular coordinate system. And so, again, to save time, I went ahead and just picked out some x values. So this is one function, f of x equals negative x. This is another function, f of x equals negative x plus 2. And I just wanted to kind of show you a few things. But I went ahead and picked out the same x values I did last time. I can pick out whatever values I want. But I can't just pick out whatever y values I want. I have to plug in the -3, -2, -1 into the function each time to get the y values, which are right here. So here's my ordered pairs. And then I did the same thing with the second function. This should be a g right here. I did the same thing with the second function, and it spat out some y values. So these are my ordered pairs. So I'm just going to take a second and try to graph these on here and show you one advantage of using function notation and being able to graph using points is we have the opportunity to compare one function with another. So if I stick them both on the same coordinate plane, I have an opportunity to like see, okay, well this one seems like it's doing one thing, this one's saying like the other. So this is f of x, this is the f of x, which equals negative x. So those are just those points right here. And maybe I should change the color for the second one. So the second one I'm going to color in blue. And you'll just give me a second to color this. I think I got all 7. Okay, this blue line is my second one. And so what I've done is I've just taken 2 functions and I've graphed both of them, and you can see, you can talk about those 2 functions. You can say, oh look, those lines look like they're actually parallel, which they are, which is cool. Also, notice the g of x function looks like it's above the f of x function. That's cool. And so what you might see as you work on stuff in this section are certain application problems where maybe it's not clear what's going on, but once you graph these functions in the same coordinate plane, you can say things like that. You can say like, this function is greater than that one. The blue one's greater than the red one, or they're parallel. They never actually cross each other anywhere. Like that's a cool thing you can notice from graphing them. And so anyway, that's just kind of something cool that pops up sometimes. And it's not a hard thing to put 2 graphs on the same coordinate plane. The last thing I need to show you is something called the vertical line test. Now the vertical line test is simply put that says if any vertical line intersects a graph in more than one point, then the graph does not define y as a function of x. So this is a way of answering the question, is this a function or not? Because not every graph that you see is a function. Not every equation that you see represents a function. And one thing, one way of testing that is by graphing it and then seeing if it passes the vertical line test. So in each one of these, we're going to see if there's any sort of vertical line that we can draw that crosses the graph more than once. And if so, it can't be a function. So here's one. And in any case, if I try to draw vertical lines anywhere, the vertical line hits the graph exactly once each time, which means it is a function. So we would say this is a function, but it never hits it twice. Here's another one. It's very similar. I can't find a place to draw a vertical line that hits the function twice, so this one's a function too. In the same way, this line is completely flat, but that's okay because I still can't draw a vertical line that crosses it more than once. So this is a function. You might be wondering, like, what the world are we doing here? But here's an example of one where something goes wrong, because here's an oval, and if I draw a vertical line right there, oh look, it crosses the function twice. Well, that violates the vertical line test. If I can draw any vertical line that crosses the function more than once, it's not a function. So that would be my conclusion here. And that's just because I found a vertical line that works. And you can, I mean, you might have to search for it, but like I've got several vertical lines here that cause problems. Well, I guess these 2 do. So that's the way we're going to identify whether things are a function or not. So that's kind of some introductory stuff that's going to get us starting on graphing. Later, we're going to learn some more tricks to help us graph maybe a little more efficiently or quickly, or graph some harder functions if we need to.